Good morning, everyone. I hope you had an awesome weekend and are ready to engage with some calculus. We're actually pretty much over the hump of the hardest material, and it should get a whole lot easier at this point. What I wanted to do today, this week will kind of be a normal week. We've got Monday, Wednesday, Thursday lecture, from what I understand. Hopefully no strange schedule changes. There will be a quiz on Thursday. The quiz on Thursday will cover some stuff on Riemann sums from section 4.2 and 4.3. It will go through the stuff that we're going to talk about today too, though, and today's stuff should be easier. Conceptually, if you've got the idea of what's going on, then the stuff we're going to talk about today is actually easier than the Riemann stuff that we were doing earlier. So hopefully that should be a little bit of an encouragement. But the material that we're going to go over on Wednesday and Thursday is actually some of the most important stuff that we're going to do in all of this year. We're going to cover one theorem in two parts over the course of Wednesday and Thursday. And that theorem is called the fundamental theorem of calculus. So that tells you how important that material is. So you'll have this lecture, the lecture, we'll record it. You can go back and look at it again. I'll explain why that theorem is important. We'll get to all of that when we get there on Wednesday and Thursday. But the nice part is that theorem makes your life a lot easier. And we all like having our lives easier. So what my plan for today was to go over one homework problem, one of the Riemann sum problems, and then just kind of I may do a quick review of conceptually what's going on with Riemann sums, then do that homework problem, and then kind of continue on with the rest of the material from this section. Okay? So let's just start with a quick review. Just a review about Riemann sums and definite integrals. And you should understand this well enough to be able to give me kind of a one-sentence summary of what it is that we're doing when we're trying to find area, and then like a 3 or 4 step summary in terms of what we're trying to do when we find area. Okay, the one-sentence summary, if I want to find the area under a function, or the area between a function and the x-axis, if somebody asked you, what is this calculus stuff about? And you said, well, one of the things that we're trying to do is find area. And they said, oh, how do you find area? The one sentence summary of what it is that we're doing is we're finding area by approximating using rectangles. Okay, that is the summary of what it is that we're doing. We're finding area under a function by approximating that area using rectangles. That's the overall idea of what it is that we're doing here. Now, the kind of 3 or 4 step process that we were doing with that when we want to kind of do this generally is number one. So I'm gonna expand this A to B just a little bit here. Number one, we divide the interval into n equal parts. I think I mentioned last time that the book tries to do this in much more generality, where the parts don't always have to be equal. That gets really confusing, and if this is your first time seeing this stuff, it's not worth getting to that level of confusion. So we're going to take this and divide it up into n equal parts. Okay, and we call these points, when we did this in general last time, I call this first point x0, x1, x2, x3, all the way up to xn, right? You remember we did that. I just want you to be able to see this a little better. Okay, and then the width of each one, the width of the whole thing is b minus a. So if this was 2 and this was 5, it would be 3. So the width we label delta x, and the way that we calculate that is b minus a over n. But in general, when I'm doing these formulas, I'm just going to keep it as delta x. Okay, and then the second thing that I do is I pick points in the interval to determine the height of my rectangles. Okay, and my points we call x1 star, x2 star, x3 star, all the way up to xn star. So I pick a point. Let me use a different color here, just so this is a little easier. I'll pick different points in here. So I can always pick the right end point, or I could always pick the left end point, or I could always pick, let's just do, in this case, I'm just going to pick the midpoints, but they don't have to be midpoints. Okay, so I'm just going to pick some points. And then what I mean by determining the heights is whatever the height is at that point, I'm going to draw a rectangle of that height. So whatever the height is at that point I selected, I'm going to draw a rectangle. Oops, that did not look good. I'm going to draw a rectangle at that height. Okay. And what I mean by determining the height is that the height of this first rectangle is what I get when I plug this point into the function. So the first height is going to be, the height of the first rectangle is going to be f of x1 star. So I take that point and plug it in the function, that gives me the height. The height of the second rectangle is going to be f of x2 star. The height of the third one is going to be f of x3 star. And then I get f of xn star. Okay? So that's how I get the height. I've got the width of the rectangles, then I've got the height of the rectangles, and then I just add up to get the total area of the rectangles. So the rectangle area is going to be the height of the first rectangle times the width plus the height of the second rectangle times the width, and then you keep going until you get the height of the last rectangle times the width. And if we were to write that in sigma notation, I've got f of x sub something star times delta x, and that something goes from 1 to n. That is the sum of the areas of these rectangles, and we call that a Riemann sum. Okay? The Riemann sum is just a sum of areas of n rectangles. And then what we do in our last step is we let the number of rectangles go to infinity. So we let n go to infinity, and what happens here is we change our notation. All of our Greek letters become Roman letters, so my delta becomes a D. My sigma here becomes an S, but elongated. I keep the f of x in there, so I have height times width, but then I put the left and right endpoints in there, and this thing now is the area. It's the limit of my sums, and it's the area, and we call this the definite integral. Okay, this is an area. Got it? And this A is called the lower limit of integration. The B is called the upper limit of integration. Okay, this is the definite integral. Got it? So overall, I'm getting the area by approximating using rectangles. The 4 steps are I determine the widths, then I determine the points to get the heights, then I add up the areas of the rectangles, height times width, and I let n go to infinity to get the resulting thing. Now, so let's do this one last time. We're not going to keep doing it and keep doing it and keep doing it. And I think that's the thing that will probably make you most happy, that we're not going to just keep having to do this stuff. There's actually a really nice way to calculate this area without having to go through limits of rectangles. I think everybody's on board with that. So let's do section 4.3. This was one of the homework problems. Number 7. And if you already did it, you can just kind of follow along and check your work. So it says, evaluate the definite integral as using the limit definition. So in other words, so I've got the integral from 1 to 2 of x squared plus 1 dx. This means the area under x squared plus 1. Okay, here's x squared plus 1 from 1 to 2. So it's that area right there. And we're supposed to do it using this limiting process. Now I told you when we did this, we're always going to use right endpoints, and we're going to do that here. So the first step we're going to do is we're going to take our interval and we're going to divide it up. Okay, so let me do that. I'm going to expand it out a little bit here, just so you can kind of see this a little bit better. All right. So the same thing happening up here. But this just kind of, think of this as a zoomed in picture here. So you can kind of see what's going on. So the overall width here is 1. So the width of my rectangles is going to be 1 over n. They're all going to be the same width. Okay. So that makes this point right here 1 plus 1 over n. This one right here 1 plus 2 over n. 1 plus 3 over n, and then that keeps going until I hit 1 plus n over n. In other words, 1 plus 1 is 2. So that works. Okay, and then I'm gonna draw in the rectangles. So let's draw a few in, and we're using the right endpoints. So I'll just draw maybe 3 of these. You don't have to draw them all in. Okay, and then the area, because we're using right endpoints and rectangles, we can call the area Rn. That R does not stand for Riemann. It stands for right endpoints. We're going to look at a few other ways to calculate this when we get up to section 4.6, but we're not going to do that right now. The point is more to kind of get your feet under you in terms of how these are even calculated at all. Okay, so we're going to take the width, which is 1 over n, times the height. It doesn't matter if you do height times width or width times height, either one's fine. And the height is what I'm going to get when I plug this point into this function, x squared plus 1. So I'm going to take x squared plus 1, and I'm going to plug that point right there, the right end point in, 1 plus 1 over n. Got it? Now let's do the second one. So I've got width is 1 over n, and height is what I get when I plug in 1 plus 2 over n into the function. Right? And then 1 plus 3 over n, so 1 plus 3 over n into the function. And then the last one is going to be 1 over n times, I'm going to plug in 1 plus n over n. Okay? So that should be how you set that up. Hopefully that makes sense. And now, let's stick it in sigma notation. So, we're going to have the sum of 1 over n times 1 plus something over n squared plus 1. And that something goes from 1 to n, so that should be your sigma notation that you're looking at. Got it? Okay, now what I'm going to do is multiply, I'm going to square out this term right here, I'm going to FOIL it. So what I'm going to get is 1 over n times, if I FOIL this out, I'm going to kind of skip writing it out and then FOILing it individually, but you're going to get 1 plus 2 copies of the cross term, so it's going to be 2I over n. And then the last term times the last term is going to give you I squared over n squared. And then you've still got that plus 1 hanging out at the end there. Okay? So 1 plus 1 is 2, so I'm going to write that. I'm going to multiply the 1 over n in, and I'm going to get 2 over n plus the 1 over n times the second term is 2I over n squared. The 1 over n times the third term is going to give me I squared over n cubed. Got it? So then let's separate the terms. So we're going to write these as 3 separate sums. So 2 over n plus, and I'm going to skip another step here and just pull out everything that's not I. So the 2 over n squared is going to come out, and I'm going to get the sum of I. And then over here, the 1 over n cubed is going to come out, and I'm going to get the sum of I squared. Okay? So now, none of this depends on I in this first sum, so that's just going to be 2 over n times, I've got n copies of them, so times n. Then I've got 2 over n squared, and then this sum of i's is n times n plus 1 over 2. And then I've got 1 over n cubed, and the sum of I squared is going to be n times n plus 1 times 2n plus 1 over 6. Okay, those were the formulas that you had before. Those are the formulas that I'm pulling off that sheet. Sum of constants, sum of I, and sum of I squared. Okay, if we cancel and clean up a little bit, got an n there that I can cancel, and a 2 there that I can cancel, and an n there that I can cancel to leave an n squared. So what I get here is 2 plus n plus 1 over n. And then down here on the bottom, I've got 6n squared. And on the top, if I were to multiply this out, I'm going to get 2n squared plus 2n plus n is 3n plus 1. And when we let n go to infinity, that's kind of our last step here. So the limit as n goes to infinity. You've done this a lot, so this may, you probably don't, I don't know how many steps you really need me to do here, but obviously the first thing's going to be 2. This n plus 1 over n, where is that going to go? We can do a little bit of formal stuff, but that's really going to go to 1, right? And this other thing, if you look at the highest powers of n on the top and the bottom, n squared on each, when n goes to infinity, these other terms are going to go away, and you're just basically going to get 2/6. If you can see that, you don't have to actually show a lot of nitty-gritty work. I'm okay with you just writing that. That's okay. So we've got 3 plus 1/3, so in other words, 10/3. That is the area that's shaded up there. The limit, it's approximating the area using rectangles and taking the limit. Got it? All right. Okay, and I guess there's one other thing that I should say about this limiting process. This always works. You always get a limit here as long as one condition is fulfilled. I didn't talk about that condition, but that condition is that if f is a continuous function on the closed interval, okay, this integral will always exist. You can always find this definite integral as long as we're talking about a continuous function on a closed interval. Now, there are situations where the function does not necessarily have to be continuous, and this still will have a limit, but we're not going to get into those right now. We may have time later on in the year to talk about that, but for now, we're only going to talk about a function that's continuous over the interval that we're trying to find the area for. Okay. Hopefully that makes sense. I'm not sure if there are any questions. My eraser is gone, so let me go grab that real quick. All right, so what we're going to talk about now, let me erase this. I'm going to leave this up here just for a second, because this is actually going to help us. The second half of section 4.3 is on properties of definite integrals. Okay, what kind of properties does this kind of thing have? Okay, when we're talking about the area of a function from one place to another, what kind of properties does this have? And as we go, you'll kind of see what it is that we're talking about. But the first thing that I have to point out is that many times there's a lot of confusion between this notation versus this notation. Okay? Now I introduced this notation earlier and I used some specific language with this. This is the general antiderivative. Okay? That's what I called this. I did not call this an integral. The book may have done that. That's kind of a mistake because we haven't related these two yet. It turns out that the two of them actually have a relationship, and that's what we're going to get to in the next lecture or so. But right now, there is no relationship between them, and I don't want you to try to slap a relationship between them. This is the general antiderivative. This is the definite integral, which represents an area. Right? So in other words, visually, this is asking what function would I differentiate to get this thing? That's what this is asking. This is saying, for this function f, between a and b, what is this area? Okay, those are very different questions. They're related, it turns out, but they're very different questions. Okay, a couple of differences that immediately come up between these two things is number one, so I guess number one, they're named different, and conceptually they're different. The next thing, number three, one of them is a function. This is a function that I'm asking for, but this over here is not a function, it's actually a number. Okay, this area, like when we did that problem down there, I didn't get a function, I got 10/3, I got a number. And that's true here. Definite integral or an area, what we're asking for is a number, we're not asking for a function. Here I want a function, or actually a class of functions, that when I differentiate them, I get this function. And that class of functions also means that all of your answers when you do these kinds of problems should have a plus C on them, all of them. There is no plus C that comes out from this kind of stuff. Okay? So please be sure that you distinguish in your mind between these two things. They're very, very different. Another thing to notice is that because this thing is an area, it's a number. It's actually a number that's independent of x. Okay, there's no so let me write this down. It's independent of x. So in other words, when I did that problem number 7 and I got way down to the answer, it was 10/3. It wasn't like 10/3 x cubed plus 4x plus something. It had no x's in it. Okay, and that's actually important. The variable that you have here doesn't end up showing up in the answer. So that means that it doesn't matter what variable is there. You could have f of t dt, or the area from a to b under f of z dz, or I used to have a calculus teacher who loved to use the variable squiggle, zeta. So he'd say this is the area under a to b of f of squiggle d squiggle. Okay? Doesn't matter what variable you're using as long as we're talking about a definite integral from one number to another number. It's just it's an area, it's a number, doesn't matter what. So you're going to see in the book different letters that are used to find areas. It doesn't matter what letter it is as long as you're going from one number to another. Okay? So please don't confuse these two, and please be careful that when you get a number, it doesn't matter what variable it is that we're talking about. Okay, make sense? All right. In very special cases, I'd love to keep this up here. Yeah, I'm going to go ahead and erase this. So in very special cases, you can actually calculate this already, calculate a definite integral without doing areas of rectangles. So let's look at 3 special cases. Where I can do this, I can actually find these areas, I can find these definite integrals without doing rectangles. So the first special case are constant functions. Okay, so if I was talking about the area from A to B of a constant, okay, C is a constant here. Let's just draw a picture for a second. I have a constant function C and I want to go from A to B. Now if I set this up with rectangles, I would be dividing up this and adding up the areas of the rectangles, but the areas of rectangles, those rectangles are just going to add up to the area of that rectangle every time. So when I let n go to infinity, it's just going to be this area. So the question is, what is this area? Well, the height is C and the width is B minus A. So this definite integral, this area is going to add up to C times B minus A. Okay, so in the case of constant functions, you can actually just write down the answer. We do not have to, unless I tell you, I can tell you, but unless I tell you, for constant functions, you don't have to go through this limiting process. Okay? Second class of functions that you can actually do without going through the limiting process are lines. So something along the lines of mx plus b, right? So if you have an integral from A to, I guess I can't call it B anymore, mx plus c. So I'm not going to do this in general. You'll see how to do it in general when we get to the stuff that's coming on Wednesday and Thursday. But just to kind of give you an example, let's do an example. If I went from 0 to 3 under the function 2x plus 1. Okay, 2x plus 1 has a y-intercept of 1 and a slope of 2. So I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. Okay, this is the area that I'm talking about right here. Now for any line, constant functions are included in lines, but for any line, you can actually always break the area up into rectangles and triangles. Now the book gets fancy and starts using trapezoids. You don't actually have to use trapezoids and remember formulas for trapezoids. Just break it up into rectangles and triangles. And if I do that, I can get what the area of that thing is without having to use approximating rectangles and Riemann sums and taking limits. So for instance, with this, the area of the rectangle it's a 1 by 3 rectangle, so the area is going to be 1 times 3. And this triangle is going to be 1/2 base, which is 3, times the height, and I just have to figure out how high up it went. So it went 2, 4, 6. So in other words, this is 3 plus 18 divided by 2 is 9. So I get 3 plus 9 is 12. That is the area under there. And I did not have to use rectangles. Okay? So in the case of lines, unless I tell you, and I can tell you sometimes, if I say find the definite integral using the limit definition, then you have to do this. Otherwise, if there's another way to calculate it, you can do that. All right? Okay, third are half circles. Half or actually even quarter circles. Okay, so This is something along the lines of, if you remember, before I show you what the definite integral looks like, if I have a half circle, so that's going to go from like negative r to r, so it might go from, for instance, if I were to do this in specific, like negative 3 to 3, and the formula for a half circle centered at the origin is the square root of r squared minus x squared. So in other words, if we were doing this in this specific case with the 3's, it would be the square root of 9 minus x squared. Okay. So the way that you can calculate this area of this specific function, you know how to get areas of circles, so you can take that in half or in a quarter to get areas of half circles or quarter circles. So I mean, if I said, what's the area from negative r to r underneath that function, r squared minus x squared dx, that would just be 1/2 of the area of the circle, and the area of the circle is pi r squared. So for example, if I said, what's the area from negative 3 to 3 under 9 minus x squared dx, this is what the problem might look like. If you recognize this is a half circle, then you'll realize that this is half of the area of that pi r squared. R, my radius here is 3. So it's 9/2 pi. Okay, and I didn't have to do any rectangle stuff at all. Notice also that I could go from 0 to 3, and if I did that, then I'm using a quarter of the circle instead of a half or the full circle. So it would be 1/4 pi r squared, so 9/4 pi. Okay? So in those specific cases, you do not have to do an actual integral using limits, which is nice. So you'll see some problems like that in the section 4.3, looking at numbers 23, 24, 26, 28, 31. All of those are examples of just using geometry to get the area instead of using rectangles. Okay, we're good to go? Does that make sense? Okay. So now, let's look at some general properties, even outside of these special cases, some things that are always true of definite integrals. And these actually will help us do some other evaluation. And these are good things to keep in mind even when we learn how to do some of these definite integrals in a really nice way. Okay, so kind of another general property is that if I take the integral from a to a of a function, that's always 0. So in other words, if I'm going from 3 to 3 or 0 to 0 or 1 to 1, if the left and right sides, if these two things are equal, the area is going to be 0. And I want you to think about for a second, why would that be the case? One reason that should be the case, one reason that should come to mind that you should think, yeah, that would be 0, is that if we were doing this calculation, I mean, number one, if these two things were equal, then there'd be no area, which is kind of conceptually why that's 0. But really the calculational reason why it's 0 is that the width of the rectangles that you're trying to add up, the width of all the rectangles are going to be 0, so the areas of the rectangles are going to be 0. And when I let n go to infinity, the definite integral is going to be 0. Okay, so if you go from a number to the same number, a definite integral that way, you will always get 0. Okay. All right. So a second property is that if the function is positive, non-negative, if the function is bigger than or equal to 0, then the area underneath it is also always bigger than or equal to 0. Okay. Now, one thing that this is this you may not have thought about this, but I'm going to state kind of a second piece of this, that if the function's negative, then the area underneath it is also going to be negative. Now, I want you to think, you might think, negative area, how does that work? Well, what's actually going on here is that we're taking widths of the rectangles, which are positive here, right? So if this was 2 to 5, I'd have a width of 3, and my widths of the rectangles would be 3 over n. But we're picking points and plugging them into functions, and if the function's positive, if it's above the x-axis, this is going to give me a positive height. But one thing you might not have thought of is that if the function's negative, and I plug these numbers into the function, I'm going to get a negative height. And a positive width times a negative height is going to give me a negative area for that rectangle. So if all of the areas of the rectangles are negative, the sum is going to be negative and the limit is going to be negative. Okay? So but if all the function values are positive, then I've got positive width and positive height, positive rectangle areas, positive Riemann sum, positive limit. Okay? So what the integral is actually doing is if the function, let's say I were to go from A to B here, what it's doing is it's considering the stuff above the x-axis to be positive and the stuff below the x-axis, the area below the x-axis, to be negative. And then what this computes, if I went from A to B, it computes what we call a net area. It's got the positive area minus, and then you're taking away the negative area. Does that make sense? So because if the function is negative, the heights of the rectangles are negative, the widths are positive, and so the overall area is negative. So if the function's positive, the area is positive. If the function's negative, the area is negative. If it flips from positive to negative, what the definite integral is calculating is a net area. So let me give you an example. If I were to look at, I can maybe do this example up here. Let's take the sine function for a second. Okay. If I were to calculate, this is pi, and this is 2 pi right here. If I were to calculate the area from 0 to pi under the sine function, okay, the area from 0 to pi under sine, let's see, I believe, if I remember correctly, I think this area ends up being 1. Don't quote me on that, I'm just doing that off the cuff. Okay, this area under here ends up being negative 1. So if I asked you, if you had to calculate this, and you don't have a way to calculate it now, but if I said, what's the area under the function sine from 0 to pi, I have to put a dx in there, that area turns out to be 1. But if I ask you the area from 0 to 2 pi, what it's going to say is, well, this area is 1 and this area is negative 1, so overall, that overall area, net area, is 0. There's a positive area and a negative area, and they cancel each other out. So this computes a net area. Got it? Okay. The other thing I want to point out about this property is that it's actually interesting that this is true. This property is true for integrals, but it's not true for derivatives. So this is just kind of a note that if a function is bigger than or equal to 0, that does not mean that the derivative has to be bigger than or equal to 0. Okay, that was not a property that we had with derivatives. Okay, so for example, I could have a function that's positive So this function that I just drew is bigger than 0. It's above the x-axis, but it's decreasing, so the derivative is negative. Do you see that? So the function being positive doesn't mean the derivative has to be positive at all. It could also be going like this. They could both be positive, but one doesn't imply the other. That's not true in the case for definite integrals. If a function's positive, the area under it has to be positive, if you're thinking of it as an area. Okay? Make sense? Okay, let's do a couple more properties here. I just like to keep this up because this helps us conceptualize what's going on here. Okay, the next one is that if I have the integral from a to b of f of x dx, and I flip the limits of integration, I instead go from b to a, it turns out that area is the negative of this area. Okay, so in other words, for example, if the area from 0 to pi under sine is 1, then the area from pi to 0, if you flip the limits of integration, what this is saying is that that area would be negative 1. The reason is that if I go from b to a instead of a to b, what happens is I have to flip these two numbers in the width. So instead of going from 2 to 5, I'm going from 5 to 2. And the widths of the rectangles would actually be negative widths, which is kind of weird to think of. But if I was going from 2 to 5, the width of my rectangles would be 3 over n, right? If I was going from 5 to 2, conceptually, the widths of my rectangles would be negative 3 over n. But otherwise, that's the only thing that changes in this entire process. So instead of having positive widths, I have negative widths, but the widths themselves are the same. So what ends up happening is when you finally get the limit, when you get the area, you end up with a negative area instead of a positive area, but the overall calculation is the same. Okay? So the moral of the story here is if you flip the limits of integration, you get a negative out front. You might think, why would I want to do that? You'll see later. We'll see situations where we're going to want to flip things. And when we do that, it's really helpful for us to know that we just slap a negative on the front. Okay. Another thing is that any integral, so if I'm going from a to b, and I pick another point in the middle, so here's my function. If I want the area from a to b, it turns out what I can do is I can take the area from a to c, and then the area from c to b. Okay, the area from a to b is the area from a to c plus the area from c to b. Now, if you draw a picture, then on this almost automatically makes sense. The area from a to b is just the area from a to c plus the area from c to b. There are a few technicalities in actually trying to prove that, but it turns out to always be true. And not only is it true when the c is in here, but even if the c is like out here, if you go from a to c and then c to b, and the reason is that going from a to c, when you go from c to b and c to b is the wrong order, you end up with negative area, and that cancels out this extra area that you got. So it doesn't matter actually if the c is between a and b or not. If you go from a to c and then c to b, that's the same thing as going from a to b. Okay? So in other words, if I told you, for instance, I have a function where the area from a to c is 10, and the area from a to b is, this overall area is 15, you can tell what that area is right there immediately. It's going to be 5. Okay. Okay. Another property of these definite integrals is if I go from a to b and I have a constant times my function, you can always pull that constant out. And the reason is, if you think about this, what we're asking for here is height of rectangles times width. But it shouldn't matter if I take 3 times the height and then multiply by the width, or I just take the height times the width and then later multiply by 3. Okay, these are just heights of rectangles times width. And whether I take 3 times the height, multiply by the width, and then let n go to infinity, or take the height times the width, let n go to infinity, and then later multiply by 3, that doesn't actually matter. Okay, so you can always pull constants out of definite integrals, constants multiplied onto the functions. Okay. Similarly, you can actually, if you have the area under the sum of 2 functions, that is just the area under the first plus the area under the second. And this should also make sense because if my height is f plus g times the width, right? If you have f plus g here times the width, f plus g times the width, you can separate those out into f times the width, all of those rectangles, plus g times the width, all of those rectangles, and then just take limits of each one. You would get the area under f and then the area under g. Okay, so in other words, kind of like we do with derivatives, we can pull out constants, and a constant multiple rule, it works here. You can just find areas under each sum individually, and the same thing actually works for differences too. So this doesn't matter, okay? So for example, if I ask you to find the area from 0 to 1 under x plus 3, you could actually do the area under x and the area under 3 separately. You don't have to do it all at once. Okay, this, and then you could use geometry, for instance, here. X looks like this, so the area from 0 to 1 underneath it, this area right here is going to, it's a triangle with area 1/2. 1/2 base times height. This is a constant function. That's a rectangle. Base times height is 1 times 3, so that area is going to be 3. So it's 3 1/2, 7/2. You don't have to do the whole function together. You can split it apart if it's a sum or a difference. Okay? That's another really useful property. All right, finally, if one function is less than another, then the area under the first function is going to be less than the area under the second function. And this should also make sense. If I've got, let's see how much room I have left here. If I've got 2 functions, here's my, the bigger one's a g. So here's my g function. Here's my f function. And g is bigger than or equal to f, and I'm going from a to b, then clearly the area under g is going to be bigger than or equal to the area under f. That's just kind of a, that makes sense if we're talking about areas here. Okay. So let me do one problem similar to a homework problem here, then we're done for today. Okay. So I'm going to look at, if you have your book, flip open to page 273. I want to look at number 42 here. And number 42 says I have a function where the area from 0 to 3 is 4, and the area from 3 to 6 is negative 1. Okay. So just to kind of give you, let's maybe illustrate this just for a second. This isn't necessarily what the function looks like, but here's 3 and 6, and I've got an area underneath the function here that's 4, and then I've got another area that has another part of the function where from 3 to 6 where the area is negative 1. Okay? All right, so now it's asking me for part A, what's the area from 0 to 6? Okay, one note, this may seem picky, but I will be picky here. Please do not forget to write the dx. The dx and the integral are kind of like parentheses around the function that you're integrating. You don't start a parenthesis and then leave off at the end of it, okay? You have to have both sides. This notation of the definite integral has to have both of these things. It might seem picky. It's very important, and you'll see, especially when we get to section 4.5, why I'm being picky about it. You can't just leave it off. Okay? So this area from 0 to 6 should be 4 plus negative 1. So in other words, that should be 3. Okay, what about part B, the area from 6 to 3? From one of the previous properties we had, that should be the negative of the area from 3 to 6. The area from 3 to 6 is negative 1, so this area right here should be 1. All right. Part C says 3 to 3. How much area is there from 3 to 3? And that should tell you the answer there is 0. If those two limits are the same, then the answer is going to be 0. And then the area from 3 to 6 of negative 5 times the function. Okay, and given our property here, what I can do is just pull that negative 5 out. And this area here was already negative 1, so negative 5 times negative 1 is going to give me an area of 5 there. Okay? So hopefully that makes sense. Yep. So I think you've got some time here. If you have some further homework questions, you can definitely ask Ms. Barabo about those. Otherwise, you can take a look at the homework for Wednesday. The homework for Wednesday covers these kinds of problems, these kinds of things here. And we'll be back on Wednesday with one of the most important theorems you're going to run into in this class. Take care. Have a great day.